Okay, welcome back to Extra Help from Mr. A, and today I'm going to be teaching you a little bit about transformational geometry. First thing we're going to do is we are going to take a look at translations. So when I do a translation, I find it a lot easier to move point by point rather than moving the entire shape. So over here we see the transformation that we want to do, which is a translation, and here's our original figure. It's labeled ABCD. So rather than try to think of this as moving a polygon like this, what I'm going to do is I'm going to move each point according to this criteria. So for my A point, I'm going to go 1, 2, 3 right, 1, 2 down. And this is going to be my new A point. I'm going to put a little apostrophe beside it and call it A prime. That's to show that it's an image and not the original figure. Next, I'm going to do the same thing with my B point. I'm going to take my B and I'm going to move it 3 spaces right and then 2 spaces down. 1, 2, 3, 1, 2. This is my new B point, and again I'll call this B prime to show that it's an image, not the original figure. Same thing with our C. 1, 2, 3, 1, 2. Here's our C point, C prime, and then D. 1, 2, 3, 1, 2. And this is D prime. Then it's just simply a matter of connecting the dots using a straight edge so that you don't lose points, because what a silly reason to lose points. And then we get the exact proportions of one side to another here that we're supposed to be getting. I'll make this my D prime. And it's really easy if you do it point by point. That's the reason I enjoy doing it point by point rather than moving the whole figure. It's a lot more simple, and you're able to make sure that the lines are in proportion to one another. Okay, so now I have added a reflection line here called reflection line L. I made it a cursive L because a regular lowercase l would just look like a 1. So that's why we use cursive L's when we're doing math. So my reflection line, again, it's a lot simpler to do it point by point rather than trying to move a whole figure at once. So all I'm going to do is I'm going to count how far away these points are from my reflection line, and then I'm just going to do the opposite on the other side. So let's start with C because this is the closest to the reflection line. It is 1 block away from the reflection line, so it's 1 block above. So on our reflection line, it should be 1 block below. So we'll put a little dot here. This will be my C prime prime because this is the second time I've done a transformation to this image. Now we'll do our D point. So D is 2 blocks above the reflection line. So D prime prime should be 2 blocks below. Okay. Next we'll do A. A is 1, 2, 3 above, and A prime prime will be 1, 2, 3 below. It'll be right on our x-axis here. And then finally, B is also 3 away, 1, 2, 3 above, so it should be 1, 2, 3 down. This is our B prime prime. And again, take out your straight edge, connect the dots as we all did in kindergarten, and you will have for yourself a squeaky door and a perfect reflection of your image. So again, my advice for you for transformations, particularly translations and reflections, is to do it point by point rather than thinking of it as an entire polygon. If you do it point by point, it's a lot simpler. We will do rotations in just a moment. So now I'm going to explain how to do a rotation. The first thing you need to be aware of with rotations is how to interpret the instructions. Generally with rotational instructions, you're going to be given a degree, so how far the rotation is going to go, a direction, which is clockwise or counterclockwise, and I've made a little note there. And then it's going to say about, and what the word about means in this context is where is the center of your rotation. In other words, if you were playing a record, where would that center of that record be? If you're talking about a donut, it would be where's the hole, basically. And then it's going to give you a point, which will be the center of your rotation. So if I go to 4, 5, which is right here, this dot right here is the center of my rotation. Okay, so we're rotating this figure 90 degrees clockwise about 4, 5. Okay, it does really make a difference where your center of your rotation is. Depending on how far away your figure is from the center of rotation, it's going to throw it into different locations, so you really need to make sure. The first method I'm going to show you how to do with the rotation is using good old-fashioned tracing paper. So what you do is you pop your tracing paper down, and I don't even bother copying the whole figure. I just copy the points. So I'm copying the vertices of this polygon, and I'm going to label them as they are labeled on the original sheet. So those are the vertices of my polygon. So now what I'm going to do is I'm going to take my pen and I'm going to put it down at the center of my rotation, which is 4, 5. Put it there and hold it. And then I'm going to rotate my my tracing paper 90 degrees. Now if this helps, you can also put an arrow pointing straight up on your sheet. Okay, that would be 12 o'clock right now. We want to rotate it so it would be pointing at 3 o'clock, because that would be 90 degrees clockwise. So I'm going to twist this paper so that my arrow is pointing directly horizontally, and we see our new points. This is where the rotation would end up. For A, or A prime, what I'm going to do is I'm going to copy down its coordinates on this sheet, because it's really difficult to lift your paper and put down the points. I prefer to write the coordinates onto my sheet. So A is now at 7, 7. B is at 7, 6. C is at 5, 6. And D is at 6, 7. And then all you have to do is take these coordinates and essentially just pop them onto your grid. There's another way of doing it as well. If you don't want to go to all the trouble of tracing it on tracing paper, this way is effective for some people, just like tracing paper is effective for some people. Some people can go between the ways equally well, and some can't. It's all up to you and what you find useful. So what I'm going to do is around the center of rotation, I'm going to draw a little grid. Or, sorry, I'm going to draw kind of like a cross here. And what I'm going to do, as the image sharpens here, I'm going to measure how far each point is away from the center of rotation. So this is my baseline right here that I'm going to be using almost like a measuring tool. And I'm going to use this line as a reference, and I can imagine this line rotating up to being this vertical line. I know that doesn't really make too much sense, and again, this method might not work for everybody. What I'm going to do is I'm going to count how far away it is from the center. So we go 1 over and 1 up. Okay? If we are rotating this, then we should go 1 up and 1 over. So my new C location is right here. We'll call this C prime. D is 2 over and 2 up. So it'll be 2 up and 2 over. That's D prime. A is 2 over and 3 up, so 2 over and 3 over. Sorry, 2 up and 3 over. And then finally B is 1 over and 3 up, so we'll go 1 up and 3 over. And you will notice that this figure is exactly the same place as we would expect it to be when we use the tracing paper. Some methods are easier than others, and again, it makes sense sometimes for some people to use one method and another method another time, and some people will never get this method, and that's absolutely fine because we have the tracing paper which helps us. Just to prove that these two figures are the same thing, I'm going to take my tracing paper again, and hopefully the vertices of the tracing paper will line up with my new image. And indeed they do. So both ways I got the correct rotation. Okay, one way I used tracing paper, the other way I didn't.
Welcome to this ongoing series on the theory of relativity. In this video, we want to investigate the topic of differential geometry, a subject in mathematics that plays a central role in our theory. I'll try to take a visual approach as much as possible. Still, math is the language of physics, and no explanation of relativity is complete without it. There's no need to follow the math in any detail, but if you are interested, more details are given in the appendix videos that are listed in the description box. Our story begins with Carl Friedrich Gauss, a fellow who was immensely influential in several areas of math and science. In 1818, he was involved in an extensive survey of the German state of Hanover, and this contributed to his interest in the study of curved surfaces, what we now call differential geometry. Suppose that you're the royal road builder and there are a couple of villages that you've been told to build a road between, and the road's supposed to be as short as possible. Where do you put it? I mean, it's not as simple as drawing a straight line because you've got hills and valleys. Do you use intuition? Trial and error? Well, a scientific approach is to develop a mathematical model of the terrain that describes it in terms of coordinates, numbers, functions, and so on. Then you formulate the path problem as a mathematical equation that you solve to get a mathematical description of the best path. Although our terrain exists in three-dimensional space, it forms a two-dimensional surface. Consider the surface represented by a topographic contour map. Position on the map is uniquely specified by two coordinates, say y1 and y2, typically longitude and latitude. The third coordinate, y3, is represented by labeled constant elevation contours. Where the contours are close together, the terrain is steep. Where they are far apart, the ground is relatively flat. We say this curved two-dimensional surface is, quote, embedded in flat three-dimensional space. It's two-dimensional because each point on the surface is uniquely specified by two numbers, y1 and y2. Of course, the y3 coordinate will have important physical consequences back in the real world. Consider the road building problem again. It might be tempting to say that the shortest path between 2 points is a straight line, so there's our road. But one look at the elevation contours and we see that this would take us over a peak, probably not the shortest path. No, the shortest path will probably be a curve that avoids the peak. And this is analogous to the picture that general relativity paints of particle motion in the presence of a gravitational field. In an inertial frame, flat spacetime, particles move along straight lines at constant velocity. But when gravity is present, curved spacetime, particles move along curves as dictated by what we might think of as a type of spacetime equivalent to elevation contours. In both cases, we're just taking the shortest path between 2 points. We're going to develop our surface model using length measurements and relating those to position on the surface as denoted by coordinate values. To get started, imagine we have a rectangular graph paper type coordinate system with 1 yard spacing between coordinate lines. An arbitrary displacement can be thought of as a displacement in the y1 direction followed by a displacement in the y2 direction. Then the net displacement s forms the hypotenuse of a right triangle, and we can use the Pythagorean theorem to calculate it. S squared is equal to y1 squared plus y2 squared. So the Pythagorean theorem is the basic tool that allows us to interpret coordinate changes as the distance between 2 points on the surface. Now we've seen in previous videos that a graph paper coordinate system won't fit on a curved surface, so we've got to consider more general types of coordinate systems. To start, assume we have rectangular coordinates, but the coordinates are not measured in yards. We still want to calculate the displacement s in yards. So, say the coordinate x1 is measured in fathoms. The Pythagorean theorem only works if the sides of the triangle are all measured in the same units. So we're going to need a scale factor a1 equals 2 yards per fathom. Then a coordinate change x1 corresponds to a distance a1 x1 yards. And suppose the other coordinate x2 is measured in feet, then we'll need a scale factor a2 is equal to 1/3 yard per foot. And a coordinate change x2 will correspond to a distance a2 x2 yards. Now we can use the Pythagorean theorem to calculate s squared in yards squared is equal to a1 squared x1 squared plus a2 squared x2 squared. These scale factors we have to employ are called metric coefficients, and they will play a central role in everything that follows. Another thing that can happen is that the coordinate axes are not at right angles. These are called non-orthogonal coordinates. Suppose the angle between the axes is theta, And we've used the scale factors a1 and a2 as before, so that the sides of the triangle are all measured in yards. The Pythagorean theorem only works for right triangles. So if theta is not 90 degrees, we have to make a right triangle with the green lines shown here. Now a2x2 is the hypotenuse of a right triangle, and we can use trigonometry to get the lengths of the green sides, a2x2 times the sine and cosine of theta. Finally, we have a right triangle with s as the hypotenuse, and we can apply the Pythagorean theorem to find s. Expanding and simplifying the expression, we end up with our previous a1 squared x1 squared plus a2 squared x2 squared terms, plus a new term that contains both scale factors and coordinates and the cosine of the angle theta. When theta equals 90 degrees, that term goes away, cosine of 90 degrees is equal to 0, and this reduces to our previous result. Now for bookkeeping convenience, we collect the various factors we've developed into an array called the metric tensor. The metric tensor is absolutely at the core of general relativity. For example, one form of metric tensor describes a black hole, another describes Big Bang cosmology, and so on. For our two-dimensional surface, the metric tensor is a 2 by 2 array or matrix, and we use subscripts that denote the elements as G11, G12, G21, and G22. And these represent those A1 squared, A2 squared, and A1, A2 cosine theta factors we saw previously. It's convenient to break the 2 times A1, A2 cosine theta factor into two 1 times A1, A2 cosine theta factors because it'll make all the math more symmetric later on. So with this labeling, our previous result for s squared can be written as G11 x1 squared plus G22 x2 squared plus G12 x1 x2 plus G21 x2 x1. And this is the Pythagorean theorem generalized to scaled and or tilted coordinates. A more compact notation is to use the capital Greek letter sigma to represent a sum, and then we have the sum from I equals 1 to 2, sum from j equals 1 to 2 of gi, j, xi, xj. We sequentially substitute 1 and 2 for I and j to get the above expression. Einstein said, let's just drop the sigmas and write s squared is equal to gij, xi, xj, with the understanding that anytime you see a subscript, say I, appear twice, you're supposed to sum over all possible values. So now we have a very nice compact notation for the generalized Pythagorean theorem. Finally, we have to consider what happens when our coordinate system is curved. Even the generalized Pythagorean theorem only works on triangles. So what we have to do is limit consideration, at least at any one time, to a very small patch of the surface over which the coordinate curves are essentially lines. Rigorously, this is only valid for vanishingly small displacements that we'll call differential displacements. That's the differential in differential geometry. And we'll denote these starting with a d, as in dx1 and dx2. Coordinate changes dx1 and dx2 correspond to distances that are represented here by little arrows. Notice that the same dx2 change, that is from one green line to the next, can represent a different length depending on where it occurs on the surface. So when we write our generalized Pythagorean theorem, now the metric coefficients, the scale factors, have to be functions of position. And notice also that the distance, ds here, is a differential distance, a very, very small distance instead of the s squared we had before. Now we have all the tools we need to figure out distances in terms of any coordinate system on any surface. One more visual aid for thinking about our distance formula. You can take the 2 by 2 metric tensor and write the differential displacements dx1 and dx2 above and to the left, and then for each metric coefficient multiply by the dx value in that row and the dx value in that column. And do that for all 4 coefficients, add the results together, and you get the generalized Pythagorean theorem, what's called the first fundamental form of differential geometry. Now let's apply all this to our path problem on a curved landscape. Suppose this surface is a mathematical representation of the landscape. In an aerial view, we lose the 3D perspective on elevation, although we can represent it by elevation contours. We want to be able to relate displacement on the map to displacement on the ground. Suppose we're interested in the black path shown here. Let's take a cross-sectional slice of the surface and view it in profile. We end up with a plot of elevation vertically versus the x1 coordinate from the map horizontally. Now suppose we go to x1 equals 10 on the map and ask what ground displacement ds results from a map displacement dx1. In this case, the ground is essentially level, so ds and dx1 would be essentially the same. However, if we do the same thing at x1 equals 30, because the surface is sloped there, we'll get a larger ds for the same dx1. These effects are what the metric coefficients account for. At x1 equals 10, g11 is essentially 1, while at x1 equals 30, g11 is something larger than 1. And we can see that as the slope of the ground gets larger, the g11 coefficient will have to also. In the extreme case that the slope is infinity, that would be a sheer cliff, g11 would approach infinity. In other words, if you fall off a cliff, you don't change your longitude or latitude, so your position on the map won't be changing, but you'll still be doing a whole lot of moving. It'll just all be in the downward direction. In fact, we'll see that this is one way to view what happens at the event horizon of a black hole. There, one of the space-time metric coefficients goes to infinity. And the interpretation is that someone approaching the horizon would perceive herself to be moving rapidly, while a distant observer would not see her moving at all. So now if we know the metric coefficients at all points on the map, we can take any path, say the black curve shown here, and go along it, adding up all the ds displacements on the ground, corresponding to our dx1 and dx2 displacements on the map, and arrive at the total on-the-ground length of the path. It's then possible in principle to solve for the shortest possible path between any 2 points. So we've looked at some examples of the way differential geometry was developed and how it can be applied to analyze surfaces. In the next video, we'll see how other mathematicians extended Gauss's work from two-dimensional surfaces into abstract n-dimensional spaces, and how this provided an ideal mathematical framework for the physical concepts Einstein had developed.
The lines L1, y minus x is equal to 0 and L2, 2x plus y is equal to 0 intersect the line L3, y plus 2 is equal to 0 at P and Q respectively. The bisector of the acute angle between L1 and L2 intersects L3 at R. Now we are given two statements in this question. Statement 1 says the ratio PR upon RQ equals 2 square root of 2 upon root 5. Statement 2 says in any triangle, bisector of an angle divides the triangle into two similar triangles. Now we are given four options. We have to choose the correct one. First of all, we see that suppose these are x and y axis. So L1 is y minus x is equal to 0, that is this line. So this is L1, that is y minus x equal to 0 or y is equal to x. L2 is 2x plus y is equal to 0, that is the slope will be minus 2. So this is the line L2 whose equation is 2x plus y is equal to 0. Now L3 is y plus 2 equal to 0 or y is equal to minus 2. So suppose if this point is 0 comma minus 2, then y equal to minus 2 will be this line. So this line is L3, that is y plus 2 is equal to 0. So according to the question, L1 and L3 intersect at point P. So this is the point P, and L2 and L3 intersect at point Q. Now angle bisector of L1 and L2 intersect at the point R. So this is the point R. Now let this point be O. Now we will redraw this triangle OPQ. So if this point is O, this is OP, OQ, this is the point R, which is the point of intersection of L3 with the angle bisector of angle POQ. So these two angles are equal. Now we know that in a triangle, if OR is the angle bisector, then PR upon RQ will be equal to OP upon OQ. This is the property of triangle and angle bisector. So PR divided by PQ will be equal to OP divided by OQ. Now we can find the value of OP and OQ if we know these points. So we will first find the point of intersection. This is clearly the origin. Now this point is the point of intersection of y equal to -2 with the line y equal to x. Now as y is equal to x and y is equal to -2, so this is -2 and this will also be -2. So this is the point of intersection. The point Q will be, this will have y coordinate as -2 because this point lie on y equal to -2. So putting y equal to -2 here, we will get 2x is equal to -2. On taking on the right hand side will become 2. So 2x will be 2, x will be 1. So 1 and -2 satisfies this equation and y equal to -2. So this is the point Q. So using distance formula, we have OP will be square root of -2 minus 0 square plus -2 minus 0 square. So OP will be equal to square root of 4 plus 4 using distance formula, that is 4 square root of 2, that is, this will be square root of 4 into 2, that is 2 square root of 2. Now let us find OQ. This will be square root of 1 square plus -2 square. So this will be square root of 5. So the ratio will be 2 square root of 2 divided by square root of 5. Now let us look at statement 1. This says that ratio PR upon RQ is 2 root 2 upon square root of 5. So this statement is correct. Now we will see the options. Option 3 says that S1 is false. So this is obviously an incorrect option. Now let us check whether S2, the statement 2, is true or false. Statement 2 says in any triangle, bisector of an angle divides the triangle into two similar triangles. This means that if OPQ is any triangle, then the angle bisector of this angle will make this triangle and this triangle similar. But we know that this is not always true. So statement 2 is false. So statement 1 is true, statement 2 is false. So option 2 is the right answer.
Hello friends, in this video I'm going to prove a very important result in circle geometry. Okay, now this is a statement, okay, or this is a theorem. Okay, theorem. Okay, what is the statement? The angle subtended by an arc at the center is double the angle subtended by the same arc on the remaining part of the circle. The sentence looks a bit difficult to understand, but I'll explain. So what they're talking about is, suppose this is an arc. Okay, so let me draw, this is, say, the arc of the circle. Okay, so this is the arc, this is the center. Now this arc is subtending an angle at the center, so you can say angle AOB is the angle at the center. Okay, so let me get a thinner pen. Okay, so this angle AOB is the angle subtended at the center. Subtended at the center. That's what we mean by angle subtended at the center. So this angle, and the same arc is subtending an angle ACB. Okay, so this is angle ACB, which is the angle on the remaining part of the circle. So angle, I can say by arc AB. Okay, by arc AB. So angle ACB is the angle subtended. Let us understand the meaning of the word. By arc AB at the remaining part of the circle. At the remaining part of circle. So let us read the question again. The angle subtended by an arc. By an arc here we are meaning arc AB at the center. That means at the center is O is the center, is double the angle subtended and the remaining. So what we have to prove is basically that angle AOB is 2 times angle ACB. This is what we want to prove. Okay, that is what the statement is trying to tell you, that this angle, suppose if this is say 2x, or we can go the other way. If this is x, if this angle is x, this angle would be 2x. That means if you take an example, say if this is 60 degree, let us say if this is 60, we have to prove that this is 120 degree. Okay, so we have to generalize it. So what I'm going to do is I'm going to draw a line. Now one thing that you can see is OA is equal to OB. They are radii of the same circle. So O is the center and OA and OB are radii of the same circle. Okay, so to prove this, let me draw one very important, one very basic theorem that you should know. Suppose if you have an isosceles triangle, okay, suppose these two sides are equal. Suppose this is triangle ABC, or let me name this triangle PQR. This is triangle PQR. If PQ is equal to PR, the base angles would be equal. So if this is X, this would also be X. That in an isosceles triangle, this is an isosceles triangle, the base angles are equal. Okay, so let me remove that. Okay. Okay, so now I'm going to draw a line or a ray from C and passing through O. Let me remove this first. So let me draw a ray. Okay, so what have we got? So now this is a ray passing through C and O. So can I say that O, these two sides are equal, or in this triangle? Okay, so let me go slowly. Let me drop this back out. Okay, now that's fine. Now in triangle AOC, which two sides are equal? I can say OA is equal to OC. Why? Because they are radii of same circle. Radii of same circle. Okay, so if radii are equal, can I say that this angle is equal to this angle? So if this is say X, I can say this will also be X. Okay. Now in triangle, okay, in triangle BOC, which two sides are equal? In triangle BOC, can I say BO is equal to CO? Again, why? Because they are radii of same circle. Radii of same circle. So if if two sides of a triangle are equal, if this and this are equal, what are the base angles of this triangle? Well, you say this angle. Suppose let me do a cross there. If this is, say, if this is y, if the value of this angle is y, the angle of the value of this angle would also be y. Okay. So now that done, you know a relation. Okay. So this angle. Okay, we can do in different ways. Now this angle. How much is this angle? This angle. The angles in its triangle adds to 180. So if this is x and this is x, I hope you understand this angle, that is AOC. I hope you can see this is angle AOC is 180 minus 2x. In the same manner, in this triangle BOC, if this is y and this is y, this angle would be 180 minus 2y. Okay. Now what these three angles AOB, AOC and BOC adds to 360. So let me write this. So can I say angle AO, so what is this? Let us name this D. Angle AOD plus angle, okay, let me name angle AOB. Not, can I say angle AOB, this is this whole angle, plus angle AOC plus angle BOC is equal to angles at a point adds to 360 degree. Okay. Okay, so what do we know about AOC? AOC is 180 minus 2x and BOC is 180 minus 2y. So can I write now, therefore angle AOB plus 180 minus 2x plus 180 minus 2y is equal to 360. So I can say angle AOB 180 plus 180 is plus 360. Then you got a minus 2x minus 2y is equal to 360. Okay, now taking all this to the other side or adding the opposite of this on both sides, I can say angle AOB is 360 minus 360 plus 2x plus 2y. So this and this gets cancelled, so I can say angle AOB is 2x plus 2y. You can factor out the 2, so you get x plus y. So I can say angle AOB is 2 times x plus y. So let us go back to the figure. What is x plus y? This is your x and this is your y. So x plus y is nothing but AOC. Okay, so let us write that. But angle AOC is x plus y. So in place of x plus y, I can put AOC. Therefore, angle AOB is 2 times angle AOC. Okay, and that's what we wanted to prove. See you in the next video.